Alright, so today we're going to be learning about Riemann sums. Riemann sums, kind of our big takeaway, is a method for approximating the area under a curve using trapezoids or rectangles at specific locations. And it's very common in AP Calculus when we have a function, but we don't actually know the equation, but we still want to try to integrate it. So we want to be able to find the area under the curve. And at best, we can use a Riemann sum, which is going to help us approximate that area. So for instance, in the given problem, we have a function with table values illustrated up top, and then we are trying to figure out the area or approximate area under the curve from 0 to 5 using the Riemann sums kind of labeled here. So there's different types of Riemann sums that we'll be going over. There's a left Riemann sum, there's a right Riemann sum, midpoint, and finally trapezoidal. And the first three we'll kind of notice all are just going to be using rectangles to approximate the area under the curve. And then lastly, as we can probably guess, the trapezoidal Riemann sum will be using trapezoids to do that approximation. So let's take a look at our first objective, which would be calculating the area under the curve using a left Riemann sum from 0 to 5 using the subintervals with intervals indicated by the table. So what we're going to attempt to do here is create rectangles, and we're going to create 4 rectangles, and those 4 rectangles are going to span the values from 0 to 5 given on our table. So one thing that I like to do kind of right off the bat is just try to draw in where these rectangles are going to be going. So I'm going to have a rectangle from 0 to 1, a rectangle from 1 to 3, rectangle from 3 to 4, and finally a rectangle from 4 to 5. So we can see, even though we're going from 0 to 5, I'm still able to do 4 subintervals. And now I'm gonna kind of use my graph here to help demonstrate what this is actually going to look like. So I'm going to create a rectangle from 0 to 1, and what makes this a left Riemann sum is that the height of this rectangle is going to be given by the left y value here. So it's going to be given by the left point. So from 0 to 1, when this rectangle comes up, it's only going to go as high as this point on the left. So I'm just going to kind of grab a rectangle, and we're going to add that in right here. And we're going to actually figure out what that area is, and then we're going to add it to all of the other rectangles that we have. So we have our first rectangle from 0 to 1, another rectangle from 1 to 3, which again, the height of this rectangle is given by the left y value. So even though we're going from 1 to 3, I'm really just concerned with that y value on the left. And if it's hard to read from the graph, we can also kind of see it up here. Then, from 3 to 4, we're going to create another rectangle, making sure that the height of that rectangle is given by the left y value right here. And then we have our last rectangle that we're going to be creating. We'll notice one thing interesting with a left Riemann sum is that our final y value on the right will actually become kind of unnecessary in our calculations. So the last thing that we have to do is actually add up the area of all of these rectangles. And again, this is going to help us approximate kind of the area under this curve over this entire time. So here, we're just going to go ahead and do some kind of basic math, basic multiplying. So this rectangle is 1 by 3, so we figure out that this has an area of 3. Our next rectangle has a width of 2 and a height of 5, so we're going to end up with 10 in this case. Then we have a 1 by 4, so again, we're going to end up with an area of 4. And then our last rectangle is a 1 by 6, so we're going to end up with an area of 6. Finally, if we just add all of these values together, we're going to figure out that the approximate area under this curve using a left Riemann sum is 23. Let's go ahead and take a look at what the right Riemann sum is going to ask us to do. So a right Riemann sum is extremely similar. And again, I'm going to start this the same way I start all of my Riemann sums, by trying to figure out exactly what those intervals are going to look like on my table. So this is going from 0 to 5. So I can see a similar pattern with my rectangles. I'm able to complete the 4 subintervals from 0 to 5. And now, once I go to start creating my rectangles, what we're going to notice is that the height of these rectangles differs along these intervals, because this rectangle isn't going to go up until this left endpoint, but because we're doing a right Riemann sum, we're actually going to continue the height up until this blue coordinate here. So we're going to grab a rectangle, and some people like to start this on the right hand side because it's a right Riemann sum, and that's mostly up to preference. So if I just go ahead and I put in all my rectangles again at this point, we'll start seeing that our rectangles are actually looking a little bit different, and we're likely going to get a different approximation for the area under the curve. Another thing that we can see, in contrast to the left Riemann sum, is that a right Riemann sum will include this last endpoint on the right, but then it won't include the endpoint on the left. So we should definitely see that pattern as we continue this. Now, if I go ahead and calculate these areas, I have a 1 by 5, so this rectangle has an area of 5. I've got a 2 by 4, so I can go ahead and calculate the area as 8. This is going to be a 1 by 6, so I end up with a 6. And then lastly, I have a 1 by 2. So I'm going to go ahead and get an area of 2 for that last rectangle. Adding them all together, I'm going to end up with an approximate area under this curve of 21. And it's extremely common that when doing left and right, we end up with different approximations. Again, it's kind of the best we can do without a function. Now, let's take a look at our midpoint Riemann sum, and this is definitely kind of tricky for some students. So a midpoint Riemann sum from 0 to 5, and we'll notice that I'm now doing 2 subintervals. So I want to be able to span from 0 to 5. And my intervals are going to be indicated by the table. So what that means is that my table should split up evenly or nicely in order to do this midpoint Riemann sum using 2 subintervals. So I'm going to go ahead and draw those subintervals. So I've got my subintervals drawn, and again, you can do them below or above just to kind of help you out. And what we're going to notice here is I'm only going to be creating 2 rectangles. And the important thing to highlight with this particular process is that the height of these rectangles isn't given by the left or the right point, it's given by the point in the middle. This is what makes it a midpoint Riemann sum. Okay? So now, once I can get this right from the table, but again, visually is going to help out as well, I'll notice that my first rectangle needs to go from 0 to 3. So 0 to 3, this is going to be my rectangle. And the height of this rectangle is given by the point in the middle. So I'm going to go ahead and create my rectangles again, but the height of that rectangle is given by the point in the middle of the interval. So because I'm given, 1 isn't directly in between 0 and 3, but it is the point in the middle that I was given, that's going to be the height of my rectangle. Similarly, from 3 to 5, and this will probably make a little bit more sense, we end up with the height of our rectangle given by that middle value. Then, just like with the left and right Riemann sum, I'm going to go ahead and calculate the area. So this is a 3 by 5, or a 15 approximation for that area. My right rectangle over here is a 2 by 6, so this should end up being an area of 12, and then once added together, end up with an approximate area of 27. Our last Riemann sum is a trapezoidal Riemann sum. A trapezoidal Riemann sum, as we can probably imagine, is the result of adding up trapezoids along our graph or along our table of values. So similar to the left and right, we're actually going to be doing 4 subintervals from 0 to 5 in this particular case. So I can go ahead and draw those intervals in so I can get a better idea of what this is actually going to be looking like. But now these aren't going to be rectangles, these are actually going to be trapezoids. So it's going to be helpful if we can actually remember the equation for area of a trapezoid. So that's going to be 1/2 times the height of the trapezoid, and then I need to do base 1 plus base 2. And one thing that's kind of confusing for students when they just start out using trapezoidal Riemann sum is this idea of a height and a base. So often we think height as being something vertical. When we actually get into this Riemann sum, however, we'll figure out that the height is actually the horizontal distance here. And most of that is going to be learned actually by drawing out these trapezoids, which, while not always an option, especially on a timed AP test, is definitely going to help students to kind of understand. So that's what we're going to be tackling here. So I'm going to draw my first trapezoid. So this trapezoid goes from 0 to 1, and it's got kind of this shape right here. So it goes from 0 to 1, and we'll notice that trapezoid seems to be a pretty accurate area under the curve. It's generally considered a little bit more accurate than a left and right, but that actually considers the function, which we're not even sure of at this point. So there's our first trapezoid, and we'll have to kind of calculate the area of that. And again, I'm just going to draw in my other trapezoids at this point. I grab kind of a straight line to do this. So then we've also got one from 3 to 4. And we have our last trapezoid over here, which is going to be this. So again, if we kind of snap back to what we were attempting to do and kind of bring this home, a Riemann sum is a method for approximating the area under a curve using trapezoids or rectangles. Clearly we're trying to use a trapezoid. So if we go back to our initial graph, we're now going to be using trapezoids to try and approximate all of this area under the curve. And we can see, as we kind of flip back and forth, that this appears to be a pretty accurate representation of that area. And now we just have to kind of go through all the calculations. So here, for our first trapezoid, what we'll notice when I'm calculating the area of this trapezoid is that this is actually base 1 and this is base 2 in this particular case. So I'm probably going to be crunching some of these numbers, but for this we end up with base 1 being 3, base 2 is 5, then we end up with 4, and again these values are just coming directly from my table. 6, and then lastly we have a 2. So if I try to get the heights of these trapezoids, so this first trapezoid has a height of 1, this trapezoid has a height of 2, and then I end up with 1 and 1. From here we should be able to kind of plug and chug in this equation to try and get the area of each one of these trapezoids separately. So I'm just going to switch colors here so we can see this a little bit better. So this first trapezoid should be base 1 plus base 2, so it's going to be 8 times the height and then divided by 2. So our formula is saying that the area of this trapezoid should be 4. Our second trapezoid is going to end up being 5 plus 4, which is 9, times 2 is 18, and then divided by 2, so we end up with this trapezoid having an area of 9. Over here, 4 plus 6 gives me 10, times my height, which is 1, and then divided by 2. The area of this trapezoid is 5, and then for our last trapezoid, we end up with 6 and 2 as our bases, so that adds up to 8, times 1, which is our height, gives me 8 again, and then divided by 2, gives me 4. If I add all of these together, I'm going to end up with 22. So this is our approximation using the trapezoidal Riemann sum, is an area of 22 underneath the curve. We can't really say right now, without knowing what the function is, if any one of these methods is more accurate than the other. But if we run through it again real quick, we have a left Riemann sum. The height of the rectangles is given by the left endpoint. We have a right Riemann sum. Similar strategy, except the height of the rectangles over any given interval is given by the right endpoint in each particular case. Then we have a midpoint Riemann sum. Midpoint Riemann sum, the height of the rectangle is given by the y-coordinate that's given in the middle of our interval. So from 0 to 3, this was the only point that we knew in the middle, and then from 3 to 5, we had this point. And then lastly, a trapezoidal Riemann sum, which really uses all of the data within our table. So we end up with base values that are equal to the y values in our table, and the heights of our trapezoid are actually kind of the difference in the x coordinates. So using all of these strategies, we can do our best to try and approximate the area under this curve. So this entire area underneath this curve, we've now kind of approximated. We've got a few different guesses for what it is. So we've got 23 using left, 21 using right, 27 using a midpoint, and 22 using a trapezoidal Riemann sum. while different, we can probably surmise that the area is around 23 or 24 underneath this curve. And we definitely had a better guess than when we were just kind of looking at this graph, or we just had these table values without a real understanding of it. So again, if we just bring home our kind of final point here, and go back to what a Riemann sum was attempting to do, a Riemann sum is a method for approximating the area under a curve using trapezoids or rectangles at specific locations.